Hi everyone. In this video, we are going to cover section 3.4, derivatives as rates of change. What I want to get out of the way first is that this section in OpenStax goes into more subtopics in greater detail than I am necessarily going to go into in this video. Know that if I don't cover it, so for example, population and revenue are covered within this section, and they start out at the beginning talking about an amount of change formula. Those things you do not need to worry about. They're not in the homework set, and I will not put them on a test. In this section, we are going to focus specifically on motion along a line. Okay, so we have this definition here to begin with. We're going to use S of t for our position function. And then we've already kind of talked about in the past how the velocity of that object is represented by the derivative, right? The derivative, the rate of change, the slope at any given point is the velocity of the object that's moving. Okay, if you take the magnitude, that's what these lines here mean, the magnitude or the absolute value of the velocity, that gives the speed of the object. And then the acceleration. Now, the second derivative, we've talked a little bit about second derivative. The second derivative is the acceleration. So is the second derivative is the rate of change of the first derivative. So if I'm talking about the rate of change of velocity, right, how much is my velocity changing at any given moment in time, that's called acceleration, right? Your accelerometer on your car is how fast you're going, right? If I change my velocity, I'm accelerating in my car. We're not going to go into it in this section, but actually, technically, the third derivative of the position function has meaning and value too in mathematics, right? It would be s triple prime of t. Again, you don't need to worry about this in the grand scheme of this course. It's just, I think, interesting. That is sometimes referred to as the jerk, right? The rate of change of the acceleration. Right? If you suddenly change your acceleration quickly, what happens in your car? You jerk forward, right? That's called the jerk. So these all have practical meanings and applications and interpretations, which is I think kind of cool. All right, so now let's zoom out a little bit and pan down to get to our first example. There it is. And in this example, we're comparing instantaneous velocity and average velocity. So we're given the equation for a ball that is dropped from a height of 64 feet, negative 16t squared plus 64. The 16, that's the acceleration due to gravity for the ball. And question A says, what is the instantaneous velocity of the ball when it hits the ground? And then part B, what is the average velocity during its fall? So here we're contrasting those two terms, instantaneous and average. So for part A, the first part, instantaneous, that is the rate of change, that is the derivative. So if my function, S of t, is negative 16t squared plus 64, then the derivative, the velocity, s prime of t, is equal to negative 16 times 2. The 2 comes down, t to the first power. You don't have to write that 1 anymore once you get the hang of this. And if you jump right to negative 32t, that's also good. The derivative of 64 is 0, so we have negative 32t. Okay, there's our derivative. And then it says, going back to the problem, that's our instantaneous velocity, going back to the problem, when it hits the ground. All right, so what does that tell me? It hits the ground right here on the graph. That's 2 seconds after I dropped this, the ball. So I want to evaluate my derivative at 2. And again, I'm plugging 2 in because that's how much time passes before the ball hits the ground. So we're going to take negative 32, oops, and I just noticed a typo here, a mistake that I made in the previous step. That squared shouldn't be there. It was a 1, and then suddenly I poofed it into a 2. That was wrong. So it's just negative 32t. Whoops. So negative 32 times 2 is equal to negative 64. And let's see, do we have units here? We have feet and seconds, so that would be negative 64 feet per second. The instantaneous velocity, the moment it hits the ground, is negative 64 feet per second. It's negative because it's falling. All right, now part B, what is the average velocity? Average velocity, that's a slope. That's a change in y over a change in x. So the path of this ball, it goes from, it starts at 0 seconds and ends at 2 seconds. So for, let's see, how do I want to write this? For average velocity, that would be s of 2, the original function, minus s of 0 divided by 2 minus 0. And one thing I want to add to part A that I should have from the beginning, when I took my derivative, that is the velocity. So I'm going to write v of t equals v of t equals. There we go. That looks a little bit better. All right, finishing up with our average velocity now, going back to part B. Sorry about the sudden distraction there. Our average velocity. All right, so what is s of 2? What is s of 0? I know my denominator is 0. S of 2, if I plug 2 into the original function, check that in your calculator. 2 squared is 4 times 16, that is 64, negative 64 rather. And when you add 64, you should get 0. So s of 2 is 0, and then s of 0, plug 0 into the function, and you get 0 plus 64. Okay. Negative 64 over 2 is negative 32 feet per second. 32 feet per second is the average velocity of this ball over the whole flight. But at the moment it touches the ground, its velocity is changing. Its velocity is negative 64 feet per second. That's how fast it's moving when it hits the ground. Okay, let's look at another example here. So this next one, we're given an equation s of t. I'm going to rewrite it down here. S of t is t to the third power minus 9t squared plus 24t plus 4. And we're also told that t is only positive. T is greater than or equal to 0. This means we're dealing with positive times, positive values of t. And this is a particle that's moving along the coordinate axis. All right, part A says find the velocity. V of t is the first derivative. So s prime of t, 3t to the second power minus 18t to the first power plus 24 and then no t, right? That'd be 24t to the 0th power, which is just 24. And then the derivative of 4 is 0. So that's our answer to A. Now part B asks, and this is something that's going to be really important. Here they're asking me a question, but it leads me, it doesn't tell me directly what to do. At what time is the particle at rest? At rest means not moving. What do I know about an object when it's not moving? Well, that's when its velocity is equal to 0. Okay, so here they're telling me what to do without directly telling me what to do. So sometimes we got to read into these problems a little bit. So we're going to set v of t equal to 0. V, that's a v, I think, of t, we'll set it equal to 0. So that looks like this. 3t squared, 18t plus 24 is 0. I think I have a common factor for each of these terms. That should make the factoring step even easier. 18 divided by 3, 24 divided by 3 is usually 8. There we go. So yeah, that makes my factoring much better. This is t minus 4 times t minus 2 equals 0. So we get t equals positive 4 and t equals positive 2. So what we find is that this object stops moving twice. It has 2 points where it is at rest, at 4 seconds and at 2 seconds. So let me write that down. The object is at rest. The object is at rest at 4 seconds. Well, actually, I should probably write the 2. Well, it doesn't matter. At 4 seconds and at 2 seconds. Like that. There we go. All right, so that's part B. Part C, on what time intervals is the particle moving from left to right, and then when is it moving from right to left? Now, to answer this question, we're going to do something cool, and this is something we'll do later on in this chapter, I think, or maybe into chapter 4 when we get into graphing functions using calculus. Okay, so we're going to make a number line for the velocity function, and I'll explain why this will be helpful to us. So I'm just drawing my number line first here. Okay, and we're going to start out at t equals 0, and I'm going to label this number line that it is a number line for velocity, and this is t, the time in seconds. And so two numbers that I'm going to put are what we got in the previous step of this problem, 2 seconds and 4 seconds. And what we're going to look at, what we're going to figure out here is between 0 seconds and 2 seconds, what is the object, what is its velocity? But I don't actually care what the actual number is for the velocity. I want to know if it's positive or negative. A positive velocity means that this object is moving to the right in a positive direction. And a negative velocity means that the object is moving to the left in a negative direction. Okay, and so what we can do is if I take, and I'll change color, I want to know what is v of 1 first. And again, I don't really care as much what the actual number is as much as I really want to know what its sign is. Okay, v of 1, if I plug 1 into the velocity function, the first derivative, 3 minus 18 is like negative 15 plus 24 sounds like maybe 9? I think 9. V of 1 is equal to 9, and last time I checked, 9 is a positive number. 9 is a positive number, so I'm just going to label in there with a plus sign. Okay, how about v of, let's plug in something between 2 and 4, pick a number, how about 3? If I plug 3 in there, this one you might want to use your calculator. 3 squared is 9, times 3 is 27, and then minus 18 times 3, and then add the 24. Again, I typed this into my calculator, and I got negative 3, and negative 3 is definitely less than 0, so I'm going to label a minus sign there. The velocity is negative, it's moving to the left. And then finally, pick a number bigger than 4, the velocity at 5 seconds. Let's see what I get there. And I'm pretty sure I get positive 9 again, and that is greater than 0, positive, okay? And so what we'll do next, and it says to do this in part D, use this information to obtain, use the information obtained to sketch the path of the particle along the coordinate axes. Okay, so everywhere that the velocity is positive, object is moving to the right in a positive direction. Everywhere that the velocity is negative, the object is going to the left in a negative direction. So think of a negative velocity as putting your car in reverse. You're literally going backwards, back out of your driveway or whatever, right? If the velocity is a positive value, you're moving in a positive direction. All right? And so the way that we will answer part D is again with a number line. So this is part D. Here is my number line. In order to start plotting the path of this object along our number line, we do need a little bit more information. Okay, I need to know some positions, some places where it is to get started. So I'm going to take some 3 important numbers in this problem, and I want to know where is the object at 0 seconds. So this is the original S function. I want to know where is the object at 2 seconds. And I want to know where is the object at 4 seconds. And I did this ahead of time, so you can check these in your calculator. But at 0 seconds, the object is at 4 on the number line. At 2 seconds, it's at 24 on the number line. And at 4 seconds, it's back at 20 on my number line. So that tells me how I want to make my scale a little bit. So I'm going to start at 0, at a position of 0, and then like 2, 4, 6, 8, 10. 4, 8, I'll throw all the numbers on there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Let's see, 16, 18. I don't want to get too messy there. 22, 24, 26, 28, 30. And that's 24 right there. Again, I'm not writing every single number on there just because it'll get a little crowded and messy. Okay, so here's how this works, the plotting the path. All right, so the object at 0 seconds, it's right here. That's where the object starts out along this linear path. And it's moving to the right. And I know it's moving to the right because between 0 seconds and 2 seconds, part C told me that the velocity is positive. It's moving in a positive direction. So it's going this way. It's going that way. And I'm going to draw an arrow on my line just to show that that's the direction that my object is moving. And when am I going to stop? Well, the next like big important thing in time happening is at 2 seconds, it stops. It's at 24 right there, right? It technically stops moving for like a moment in time. That's where in part B, we said the velocity is 0. It stops moving right there. Okay, for just like a fraction of a tiny bit of a second, because it's going forwards, and then suddenly now it's going to start traveling backwards. Okay, it's traveling backwards at until I get back to 20. Okay, so it took 2 seconds to make that little tiny bit of a trip. The first 2 seconds was the long blue branch. The second 2 seconds was this much shorter blue branch, right? At 4 seconds, it's right there. And then we know that it turns around again because the velocity now starts moving in a positive direction again. And I'll draw my arrow there and add on a couple labels. That right there is at t equals 4. That right there, t equals 2. And that point right there, t is equal to 0. So the blue line represents the movement of the object as time passes. Okay, there we go. All right, so that is it for 3.4. Just this one key topic in the section. That's all we're covering. So work on some homework questions for this section. Let me know if you run into any problems. As always, thank you very much for listening. Have a wonderful day.